Welcome back. This is an Aleks homework video on calculating entropy change using the Boltzmann hypothesis. So Mr. Boltzmann, a Russian fellow that did a lot of work in thermodynamics, he was able to basically say what's happening as gases and liquids and interact with solids and what's going on energy-wise. So this looks like a much harder question than it is. If you remember what the Boltzmann equation is, it is the change in entropy, that's the capital S, is equal to a constant, that's the Boltzmann constant that you can look up in the Aleks data tables, times the natural log of W. And W is the adsorption sites. And adsorption is a word we don't use very much. It just means location places for a thin film to form. So for instance, if you were to have a piece of plastic and you have a thin film of liquid water that would settle on that plastic until it dried, that would be adsorption. It's essentially sticking to that plastic. Well, in this case, you've got a certain amount, let's say, of the plastic or some other substance that has a thin film of gas or liquid attached to it, and you have more of it opened. Okay, so instead of, in this first case, they've given you 400 sites, and then it expands to open up to 484 sites. So let's say you have a crumpled piece of aluminum foil that as it's relaxing and opening up, you have more places that water or gas could attach to. You're changing the amount of places that you could put something. They're asking for the change in entropy. All right? Well, if entropy, remember, is the amount of thermal energy that cannot be used to do work with. So think of it as chaos, or the idea of just the amount of unusable energy you can't get back somehow. The more space you have, the more entropy you're going to have, because you have more place for it to be random. The less you have, the less entropy you're going to have. So the first thing I would keep in mind is if you have less sites than you once did, you're going to have a negative entropy. If you have more sites, you're going to have a positive entropy. The more places you have for a molecule to stick to, the more random places you have to put it, then the entropy is going to expand or get bigger. So if you know that the natural log of W in this case is being replaced by the fractional part, so the W that you have at the end divided by your original W. So my original W here is 400 adsorption sites. And my W is the larger number of 484. So I'm just going to write in Boltzmann's constant. So you can get this from the data tables. So 1.38065 times 10 to the negative 23rd joules over kelvins times the natural log of the fraction of 484 divided by 400. Now notice that 484 over 400 is getting bigger. It's a number bigger than 1. And just a little bit of review on natural logs. If you have a number bigger than 1, you're going to have a positive natural log. The natural log is going to be a positive number. And then when you multiply that by the Boltzmann constant, you're going to have your entropy will be positive. If it's exactly 1, then there's no change in entropy. Because if you have the same amount of sites at the end that you had to start with, you didn't change anything, and so you're going to end up with 0 times Boltzmann's constant, and your change of entropy would be 0. If you have a number less than 1, you're going to have a negative entropy. So as the sites reduce, your entropy would be negative. As the sites increase, your entropy will be positive. And then you multiply those two numbers together. In this case, I had to take 3 significant digits and end up with 2.63 times 10 to the negative 24 joules over Kelvin. So actually ending up a pretty simple problem as long as you have your formula. Wish you well.